test 2. And it's sections 3.3, 4.1, 4.2, and 4.3. Okay, the majority of the test, I'm going to tell you now, the majority of it will focus on 3.3. I would say like 65% of the test would be from 3.3 and 35% of the test would be through those short sections we did in chapter 4. Okay, so the majority of the test, say 2/3 of it, will be from section 3.3. That's the section that took us a while on projectile motion. Okay, the one that we worked on the lab on, spent a bunch of days in class, and then you also worked on most of those in the problem set. All right, so from 3.3, let's begin to review this. I want to talk about it. I want to do an example problem, mathematical example. What are some of the things in section 3.3 about parabolas that you maybe have written down in your notes? Or some key points that you've come up with or understandings based on the end of that lab? What were some of the ideas of projectiles? Some concepts that you might want to think about? What's one important piece of information from section 3.3? Could be anything. Just open-ended. Just asking you guys to respond.
The air resistance?
Air resistance. So what about it?
So if there is air resistance, it will not go as far as if there were no air resistance?
Yeah, air resistance really affects the motion of an object. Without air resistance, it follows a perfect parabola that's symmetric. With air resistance, though, it wouldn't go as far, nearly. Okay, it would end up being asymmetric as well. What else? What else from section 3.3? What else? You didn't learn anything else in section 3.3? That was it? Doesn't matter, open it.
Trigonometry.
Okay, so what about that? What about the sine and cosine stuff?
When there's an angle involved, you have to use.
Yeah, when there's an angle involved and a launch angle, for the x component you have to do, if you recall this information, you have to remember that the velocity in the x direction is the velocity times cosine of theta. The velocity in the y direction is the velocity times the sine of theta. Good, Sarah, good. That's another point. All right, the first point that Julia made was that a projectile that moves like this, and then if air resistance is taken into account, I'll draw the blue line below it. It might look something like this. All right? So again, without air resistance, this is without air resistance, the outer line. The inner line would be with air resistance. Peter, what else?
We never use air resistance, right?
Yeah, in the problems, mathematically, we never use air resistance. Very good. You assume it's 0. Peter, by assuming that air resistance is 0, what does that help us with in the mathematical part of the problem? If we assume air resistance is 0, right, or negligible in these problems, what fact does that give us? There's one piece of information that comes from that. It's very important. If I'm running, right, and there's no air pushing me back, there's nothing stopping me this way. What do I know about something in the x direction?
Only one force.
Not force. You could relate it to forces, but specifically in section 3.3.
Constant.
What?
Constant velocity.
In the?
It's at equilibrium.
Technically speaking, yes. You're going on to chapter 4. What's at a constant velocity? You said it.
The projectile.
Okay.
Velocity.
Kind of close. You're making a small, not mistake, but you're not being specific enough. When we look at the x direction, and we look at the y direction for these kinds of problems, what did we assume in the x direction?
Gravity.
We only used one equation in the x direction. Remember, only one equation. What was the equation in the x direction we used? Always.
X is equal to velocity over time.
Other way around. Velocity equals.
Just place it over time.
Yeah, we used this equation in the x direction always, remember? Why were we allowed to use this equation?
Because velocity is constant.
Because velocity is constant, that's what Johnny was mentioning, specifically in the x direction. So if the velocity is constant, we assume there's no
Air resistance?
Sure, but again, that comes from the other way around.
Acceleration?
Yeah, there's no acceleration. The key is to remember that because there's no air resistance, there's nothing slowing it down in the x direction. But there's nothing speeding it up in the x direction. So we always assume that the acceleration in the x direction was 0. When the acceleration is 0, that allows us to use this equation. That's the equation we're always going to use in the x direction. Okay, because the acceleration is 0, because we're saying there's no air resistance. Now, although there's no air resistance, there is acceleration in the y direction still, due to gravity. Due to gravity. Okay, so the y direction still has acceleration. What else? What other pieces of information from section 3.3 did we learn? What about something you learned from the lab in section 3.3? What was one piece of info that you gained?
How to find a range?
How to find the range? Okay, specifically? If we were looking for like maximum range, what do you know?
Max height. Estimate. You guys have an angle of 45.
Yeah, Dirk, very good. It's got to be an angle of 45. Remember, a maximum range problem has an angle of 45. Now, what about this? What if the angle is bigger than 45? It means
The height, the distance traveled will be greater.
along the path. Yeah.
I'm saying it's supposed to displacement.
So you end up going on like a curved path a little bit higher up. Now, what about a lower than 45 angle?
Line drive?
Yeah, it's like a low line drive. So when the angle is bigger than 45, there's more vertical velocity. When the angle is lower than 45, there's more horizontal velocity. Okay, we talked about how that works and how the angle changes. But at 45, VIX and VIY are the same when it's at 45. And that's what gives us the maximum range of a projectile, 45 degrees. Okay, that was part of your lab.
Is that always, that's not always, only without air?
Without air resistance, it's true. With air resistance, then you have to take into account that it's not going to be, it's like, I think it's a little less than 45, like 42 or 43. Okay, something in that range.
Always? What if it's a long?
It depends. It depends on the problem. It depends on the surface area of the object. It depends on the wind speed. There's so many different things that come into account. I'm just giving you from the lab, I think it was something less than 45. Anything else in this section? What about the velocity of an object when it's at its peak? What did we talk about? So here's the object, ready? It's following this path, it's following this path, and now it continues down. At the peak, what do you know, Marco?
It stopped.
What part of it stopped though?
The velocity,
Which part?
acceleration.
Stop, don't just stay right there.
No.
Which is not? Which part stopped when it reaches its peak?
Oh, it's Y.
It's y velocity, or it's vertical velocity. Remember, as Johnny told us a minute ago and Julia reinforced, the horizontal velocity is constant because there's no acceleration. Look at this formula right here on the left. The velocity in the horizontal component, x, is not a function of acceleration here. There is no acceleration. So whatever the velocity is horizontally in the beginning, it remains throughout the entire problem. But on the way up, it's got to stop to come back down. So the vertical velocity is 0 at the top. The vertical velocity. The horizontal velocity is the same the whole problem. It's whatever it was from this equation right here, or from this equation up here.
So
Peter.
vertical velocity.
Wait, when it's VI, and VIX, VI is the same thing, and that's given in the column, right?
Usually the VI is given in the problem. Usually. There was a problem where you had to find the VI we did in class.
And so that's just VI. So VIY would be the velocity right when it started. Obviously.
Right when it started, vertical velocity is VIY.
And then
VIX,
it becomes 0 eventually.
so the velocity, so it's launched like this, right?
Yeah.
Initially it's got a positive vertical velocity. It's still positive, it's still positive, it's going up, it's going up, it's going up, then it stops vertically, so the velocity vertically is 0, then the velocity vertically is now negative, becoming more and more and more negative on the way down. The horizontal part, if you remember, if it's fired at a velocity, let's say horizontal velocity is like 7 meters per second, it's the same throughout the entire problem. Okay? So this is a constant right here.
That doesn't change.
Okay, whatever you figure out it stays the same the whole problem. Whereas this part is clearly changing. Okay? I was going to say it's a variable, but I don't want to use the word variable with variables.
Can you use VIX from like every projectile motion problem?
Whenever it's launched at an angle, you're going to need some sort of VIX and some sort of VIY in those problems. Okay, whenever it's at an angle.
Okay, so you said that VIX is 0 at the peak of an object's travel.
VIY is 0 at the peak.
Oh, so then what happens to X?
VX is the same throughout the whole problem. And it's not VIY, it's just VY, really. Because I stands for initial, and at the peak it's not initial anymore. Hey, we also talked about a type of problem where an object could be fired horizontally from a ledge or from a given height. And when the object were fired horizontally, it still follows a parabolic path, just only half of the parabola, right? Just only half of it. And then we also talked about, well, what if an object is dropped from the exact same height, which I should make that better, hold on. From the exact same height, an object is now dropped and it falls down. Okay, what did we conclude about these two? What piece of information, Peter, did we conclude?
The initial velocity of y is 0.
They're both VIY 0. Very good. Remember, if I drop an object, its initial velocity has got to be 0. It's starting from rest. If I fire an object horizontally, it means it's all horizontal. There's still no vertical velocity. So in both of these scenarios, VIY is indeed 0. Good, Peter. What can I draw from that? What statement can I make from that part? There's always no horizontal acceleration, but there's definitely vertical. We did this with the tennis balls. What was the goal to see in that? They land at the same time. The time it takes for an object to fall from rest to a certain location is the exact time it will take an object fired horizontally, assuming they were at the same height to start. So again, if I shoot a bow and arrow and you drop a rock, technically speaking, it will hit the ground at the same time, provided the bow and arrow I shot was fired horizontally from the same height you dropped the rock. All right, let's see. That's it theoretically. Okay, that's it theoretically. Let's go to a math type problem for this. Now, let's take a look at a mathematical type problem. Let's say an object is fired from a cliff. We'll start with one of those. With an initial velocity of 20 meters per second. And the height of the cliff is 100 meters. And we want to figure out how far it goes, or find the range. What does range mean in physics? The x displacement. Very good. X displacement. So please don't let that confuse you with range in math, because range is the y values that the function can take on in math. When it says find the range of the projectile, it means find out how far it traveled horizontally. All right, so we're looking for x in this problem. What else do I know? What else can I write down? Go.
A is negative.
All right, that's true. What's the y value going to be in this problem?
Why isn't it negative?
What is it?
Negative 100
Yeah, be confident. Where did it start?
from the top.
And it moved down, so it's got to be negative, right? Okay, we're looking for x. That's unknown still. Now, what's the VI in the y direction? In the y direction. I heard 20 and I heard 0. Which one is it?
X isn't VIX 20 and 0 is VIY.
Yeah, look, which way is it fired? Isn't it fired horizontal only? This is not at an angle, so we don't even need the cosine and the sine stuff. So since it's fired horizontally, it's always going to be only in the x direction there. The y direction is going to be 0. Remember, I launched something horizontally. It's all horizontal to start. Sure, it's going to pick up velocity vertically as it falls to the ground, but the initial velocity in the y direction is definitely 0.
Wait. Can you repeat that? You were just talking
The object is fired only horizontally, so the velocity is all in the x direction. So whatever the velocity was given as, which was 20, that will be what the x is when it's fired horizontally. Okay? But vertically, it's not really moving to start. Again, I take a bullet and I shoot it out of a gun. It starts out leaving the gun like this. It's not shooting down at all. It's not shooting up at an angle. It's literally shooting only in the x direction. So VIY is 0 to start. Now remember, you can always check this. You could check this by saying VIX is really 20 cosine 0. And VIY is really 20 sine 0, because the angle is 0 degrees now, isn't it? And this turns out to be 0. And this turns out to be 20. Because cosine of 0, this is actually 1. And the sine of 0 is actually 0. So this becomes 20 times 0, which is really 0. And this is 20 times 1, which is still 20. So if you ever forget how to do this, just assume the angle is 0. And you could still use VIX as VI cosine theta and VIY as VI sine theta, if you wanted to check.
So without checking, you would just know that DIY is 0 because...
It's fired horizontally. Okay, again, the object has been fired horizontally, so I don't really need any of this information. So I really don't want you using this information this way. Okay, it takes more time to type that in and go through the problem. You should know off the bat, okay, just from the problem, if an object is fired horizontally, you should know automatically that this is true right here. Whenever an object is fired horizontally, that is always true. VIY is always 0 when it's fired horizontally. If it's fired at any angle, you have to use what we know with VIX and VIY being cosine and sine parts. What's the linking variable that's missing?
T.
All right, in the x direction, I want to find x. I could start with my formula. But the problem is that I don't know time and I don't know x, so I don't have enough information. But if I were to solve that one for x, what would it look like, just to show the solution to it? Solve generically for x in this equation. What would it look like solving for x? Kian? Say again? You would only switch them if you were trying to find time, right? But you're trying to find x. How do you get rid of that time? Kian? It's being divided by time, so multiply both sides by time. Okay, that gives us the generic solution for x right here. That's our generic solution for x. X equals time times the initial velocity. We have the initial velocity, that's 20 right here, right? VIX is 20, but I don't know the amount of time that this problem takes to land and hit the ground. So if I don't know time, where do I go?
To the
Y
side.
side.
To the y side, because time is the same in both directions. In the y direction, I don't know anything about final velocity, so I'm probably not going to use VF or VF squared formulas. So what formula am I going to use then?
You could do VIY equals VIX. Yeah.
Okay, be careful. I think you're using the wrong one first, okay? That's what it should look like. Again, we don't know anything about VF in this problem. We're not given any information about the final velocity of this particle. So we go ahead and use this formula to start to make it easier on us. Okay, now, I know VIY is 0, so this piece drops off, which makes this problem a lot easier. If it didn't drop off and you were solving for time, you would have to use the quadratic formula, because t would be in 2 spots, but it's not in this case.
Maybe just jump to that equation.
Could you jump into the other equation? You could.
No,
If you,
no, I mean like the simplified thing to get T. Do we have to write it all out?
if you know the other equation, t equals 2y over a under the radical,
Yeah.
you could write that down, sure.
It's always going to be that though, right?
When it's fired horizontally, because this is 0, this will always solve to look like this when it's fired horizontally. Okay? The minute that's at an angle, this is not true. Now, you should still write this formula to start though, Jack.
Yeah.
Right here, okay?
Yeah.
But then you could skip this step if you want to and jump right over here. So 2y over a, you get 2 times negative 100, all divided by negative 9.81, underneath the radical. So that should be 200 over 9.81, square rooted. What do you got, Peter?
Wait, when you say 2y, is that?
It's a variable y.
Oh, okay, alright.
It's not a, this is a little subscript down here for ay.
Right.
Okay, right down there at the bottom, that's a little subscript. That's a subscript for y, that's the variable y.
$20.39.
20.39? Did you take the square root or no?
Oh, no.
Take the square root of that.
4.52.
Sounds good. Is that right, sir?
Yeah.
Okay. So 4.52 seconds for this object to hit the ground. If the object were dropped like this, it would take 4.52 seconds. If it were launched horizontally, it would take 4.52 seconds. Either way, it's going to take 4.52 seconds. Now, I take that time, I use it in the x direction over here. 4.52 times the velocity in the x direction will give me the range of this projectile. So 20 times 4.52. It's going to be a little under 100, right? 20 times 5 would be 100. So around what, 90? Okay, that is the range of the projectile. Again, this is a problem where the object is launched horizontally. Launched horizontally. Now, what if it's launched at an angle? Let's do one of those. All right, let's say an object is launched
Meters is the time it would take, no, not the time, it was how far it would be.
horizontal. Yep. So let's say an object is launched from ground level, from a catapult, at an angle of like 35 degrees. And the question we're going to see in a minute is whether or not it's going to make it up to this ledge. Okay, it's launched at a certain angle, and we want to see, will it make it to that ledge? God bless you. Okay, we know that the ledge height is 50 meters. We know that the horizontal displacement, this is not drawn to scale at all, because I'm going to put a much smaller number here, is 20 meters. It's got an initial velocity of 30 meters per second. Let's see how this works. Who knows? The question is, will it make it up to the cliff? This is a problem where you're giving too much information. Remember the problem with Tom Cruise jumping from one building to the other? We wanted to see if he would cover that gap. We didn't use all the information in that problem. It's a similar type of problem. We are trying to figure out if the particle will reach the cliff. So, what information is extra in this problem right now that we're not going to use until the end of the problem?
The height of the
The
cliff.
height of the cliff. The height of the cliff is what we're going to compare our answer to. If we figure out that the height of the projectile is 70 meters, then it's more than 50, so it makes it up to the cliff.
What is the question?
If we get a height of the projectile to be 20 meters, well then it didn't make it up to the cliff. It only hit like right here on the cliff. So the question is again, will this projectile make it to the cliff? Or will it land on the cliff, right? Will it make it somewhere on there? I don't care where it lands on the cliff, it's whether it does or doesn't. That is important. So, we know the following. We know that the x direction is going to be 20 meters for sure. There's no other way. We're trying to figure out where is this projectile after 20 meters. So, does the projectile follow this path? Does it follow this path? Does it follow this path? The question is, where is it when it reaches the cliff? So, is it going to be here? Maybe at 30 meters height, and it doesn't make the cliff. Maybe here it's at 45 meters and it just misses the height of the cliff. Or maybe when it gets to this part, it's at a height of 60 meters, so it makes it. So our goal is to figure out what the y value is at that given point in time. At the instant it passes that vertical plane, so if you were to extend the plane of the cliff vertically, the minute it passes this location, where is it vertically is the question. What is the y value? Okay, what is the y value? Now, as a result, we have to take a look in our x and y direction. go ahead and we break this up into two components again. In the x direction, VIX is VI times the cosine of theta. VIY is always VI times the sine of theta. Yeah. X is cosine, sine is y. Yep. Again, if the angle is given here with respect to the horizontal, if you're given a vertical angle, right? If you're given the angle here instead of this angle here, you'd have to find the complement and use the horizontal. Always using the horizontal angle. You could come up with those numbers and just type the, or just write them down to get rid of this. So what do we get as our numbers for those two? What does VIX really turn out to be, and what does VIY?
4.57 VIX. And VIY is 17.21.
Thanks, Jack. Okay, and that is definitely right, or I know at least it's reasonable. I'm going to cross these off now. I don't need this anymore. Once I've evaluated, I don't need it there, so don't use both, obviously. I know there's more VIX than VIY. How come?
The degree is less
Then
than 45.
the angle is less than 45. Here's 45. If it's less than 45, it's going to be more horizontal. So VIX is definitely bigger than VIY in this problem. All right. I also know the X displacement is going to be 20 meters for sure. That's where we're trying to locate the Y displacement, though. The acceleration in the Y direction is still negative 9.81.
Is acceleration ever positive?
No. The only time we're going to use G as a positive value is when we start looking in section 4.4 with forces. And that's because of the free body diagram nature. But no, for these projectiles, it's negative because it's pulling down on it. So I know VIX, I know X. What can I figure out then in the X direction? I can figure out time. Again, look in the X direction in this problem. I know VIX, it's right here. I know X, it's right here. Plug them in these two spots and find time. Or to find time, just remember switch. What does that give me? 20 over 24. It should be around 0.8.
0.814.
0.814. Now, again, I put on your test around an answer at the end to the nearest tenth, unless specified otherwise. That doesn't mean you should be rounding this to 0.8 and rounding your velocities to 24.6 or 17.2. Please keep as many decimals as you can during the problem. It's at the end that you round. Some of you are still forgetting this, that whole idea of a cumulative error. If you round early in the problem, your answer in the end is going to be way off because you made several rounding answers. So you're approximating and then approximating that and then approximating that. So they're going to be cumulative, those small deviations. So here I would keep 0.814. I would leave all three of those for sure. Even if you had a calculator, I'd probably store the answer. 0.814, 2589, whatever it turned out to be. All right, but now, what am I going to use with this time? How am I going to utilize it? Because that's not the problem. It didn't say find the time it takes to reach the cliff.
You're going to take it over to the Y side.
I'm going to move it over to the Y side. And since I'm trying to figure out what Y is, I'm going to probably use the formula Y equals VIYT plus 1/2 AYT squared.
Do we need to put the little y's when we're doing it?
No, again, if you separate into X and Y directions, that's fine. I'm just putting it to be, careful. At this point in time, all we need to do is plug into this equation. VIY is 17.21. Okay, that's 17.21 times the time of 0.814 plus 1/2 times negative 9.81 times t squared.
Do you mind if we skip and just go straight to negative 4.1?
Sure. Just make sure you squared the 0.814, please. Square that, then multiply it by the negative 4.905, or half of negative 9.81. What did you end up getting for y in this problem? It's probably not going to make the cliff just by estimating these numbers in my head. It's definitely not going to make the cliff.
7.6.
Yeah. So it turns out that if I look at my original diagram, here's the original diagram. Well, let's make the cliff on this side. Here's the cliff over here. Here's the object. The object hit the cliff over here at a height of 10 meters. Okay, the cliff was a height of 50 meters, really. The object was launched at that angle. It never made it up to the top of the cliff. It probably did this. It most likely actually went like this and came back down and hit the cliff. Okay, but either way, when it was at a height of 20, at a horizontal location of 20 meters, the height was only around 10.76 meters. So it didn't make it to the cliff, or didn't make it to the top of the cliff.
Could it also have been done where you made y 50 meters and then you solved for, or no, you made, yeah.
I don't think it would have worked, because I think you would have gotten an answer. If you made y 50 meters, I think it's impossible to get to 50 meters based on the beginning of this.
Right.
So I would do it the other way always. Yeah. Peter, I get what you're saying, and if a certain problem, if it did work, it would work that way. But for problems that it doesn't make it, it won't work going the other way. Okay? It's a good question. Way to think about that. Other types of questions that you might wonder: what time it takes to get to max height for a projectile. Say the projectile is launched at an angle of 30 degrees with an initial velocity of 15 meters per second. And the problem asks you to find the time it takes to get to max height. Let's say that we also want to find the max height itself, to make it a little more complex than just that. Okay, so now we look at the problem like this. Ready? Here's the full path of the problem, but what do we care about? If we're trying to find to max height? Yeah, right here. So really, this problem is segmented. I only care about the first half of it. So if we're trying to figure out what the time it takes for this object to get to max height, we could simply look in the x and y direction and think about it. If I think about the end of the problem being at that max height, okay, I know what these are. We can figure these out, right? 15 sine 30. This should be second nature by now, especially after those problem sets. 15 cosine 30, that's always going to be that way to start. I don't know anything about the x. I don't know anything about the time. All right? So those are unknown. So the x side is pretty useless right now. What do I know about the y direction, though? Something in the y direction that's different that we haven't usually used. You might have done this on one of your problem set questions. You most likely did, if you did it right. To find the time to get to max height, oh, you're on the right track there. If we find the max height time, we can double it, get the full time at the end. The theory's right. But how do I get the max height time? How do I get the time it takes to get to max height?
Well, you know that the velocity at that time of y was 0.
Yes, Peter, very good. VFY is 0. Because at the top, remember, ready? It's got to pause vertically. Then it starts to become negative. So the final velocity in the y direction is 0 when it's at max height. Again, call this final up here. This is initial down here. I don't care about the rest of the problem. I don't care about this piece. Doesn't matter for the question I'm asking you. That's the key that we have to know. Good job, Peter. We got to know that. Now, if we know that, there's a specific equation that we can use that involves VF, that also involves time. What equation is that? I know, a lot going on, Jack. Marco.
Is it A equals VF minus VI over T?
That's a good one we could use, but we have a variation of that, which is the same thing.
Right. VI plus AT equals VF.
Yes, very good. Okay, VF equals VI plus AT. This was one of our 3 formulas involving acceleration. We know what VF is, it's 0. We know VI, it's given, we can multiply it. We know acceleration, we can find the time it takes to get to max height.
Are these formulas going to be on that formula sheet?
They are on there already. Okay, remember, the formulas on the formula sheet don't have subscripts. They just say VF equals VI plus AT, or X equals VIT plus 1/2 AT squared. You need to adapt them depending on the problem you're working on. So I put in 0 here, or I could solve this for time if I wanted to, but this becomes 0.
We never actually saw it.
VIY, sine of 30 is a half, so this is 7.5, it turns out to be. It's one of the common ones that I happen to know.
It's 1.
Okay? Sine of 30, yeah, that's why I picked 30, just to make it easier for this. Okay, sine of 30 happens to be 1/2, and half of 15 is 7.5. So I know that this is 0. I can solve for t algebraically, or I can plug in. I don't really care, I told you that. Okay, especially a problem like this where it's very simple. Okay, 0 equals 7.5 plus negative 9.81 times time. Move the 7.5 over by subtracting it, and divide by negative 9.81. What do you get for time?
0.76.
Point.
76.
So almost a little more than 3/4 of a second it takes for this object to reach max height. What if you wanted to figure out what that max height was? What if you wanted to physically figure out what is the height in this problem? Summer.
Go to the x and use the formula x equals.
Not even necessary.
No.
I'm asking for the vertical height. If it said how far does it travel horizontally after that much time, you'd try to find x, right? You could plug the time in, you could find x. But I'm asking for the vertical height that it's attained at this point. Dirks.
Use y equals DIY t plus 1/2 AY t squared.
Very good.
And,
Keep going.
and so you plug in 0.76 for all the time. I don't.
The initial velocity was 7.5.
Alright, 7.5, and then you plug in acceleration, which is negative, which is gravity, and then the time again.
Okay? Think about it for a second. You found the time it takes to get to max height. So if you want to find the height at that point, use that time. Use the time it took to get to max height. Okay? Use the initial velocity in the y direction and figure out what the height is at that given instant in time. Alright? Now, follow-up question. How long would it take for this object to land from the beginning of the problem to the end?
Double it.
Double 0.76, right? If you double this, it will land after that much time.
So when you find y,
Do you ask, sorry.
when you find y and then that, what does that mean?
That's the height of the object at max height.
Right, but is that answering any questions? That's the height of the object at max height, and then how long it takes. You just double the time.
To get the total time of the whole trip, sure. That would, if that were a follow-up. Depends on what's being asked.
But to get the time it takes to reach maximum height, that's the t that we found.
Right there.
Yeah.
Yep.
You multiply that.
What do I get for y? Anybody do this?
Oh, yeah, I did 2.87.
2 point,
87. Well, 869.
Yeah, 2.87.
okay? 2.86, 2.87, whatever it was, 87 meters, right? There are many ways these problems can vary. You need to adapt. What time is this over?
37.
Alright, so the thing I want to mention is that at the end of the test, you're going to definitely be given a choice of 2 problems. You pick one of 2. Okay, you're going to have 2 problems in front of you. You pick one of them. You're not going to have a lot of these problems at the end of the test for the math. I'll tell you now, you'll have one math problem from chapter 4. Okay, the basic one. With like F equals MA, remember we did those problems in section 4.3? Okay, then you'll have 2 from chapter 3.3. So So that part of the test alone, you're going to have one horizontally fired. I guarantee you I'll do a horizontal and one at an angle so you can see the two different types. Angle could be up, the angle could be down, it could be whatever. So that's two problems like that. One from chapter 4. That alone is like 25 minutes of your test right there. Okay, there's only going to be, I think, like about 8 multiple choice, not many. And then only like 4 short answers. So a lot of the time you're going to spend is going to be on the last part of the test, the math part. Keep that in mind when you're doing this on the test tomorrow. The stuff from chapter 4 that I want to reiterate real quick, you need to know Newton's 3 laws for sure. Okay, inertia, meaning an object in motion tends to stay in motion, or an object at rest tends to stay at rest, unless acted upon by an outside force. F equals ma. And then for each action is an equal and opposite reaction. You need to know those 3 laws, whether they're given in multiple choice or short answer, being able to recognize them. You don't have to memorize which one is the first law or the second law. It doesn't matter the order of them, please. You need to know from that section that equilibrium exists when forces are at balance. And when the forces that are at balance, it means the net force is 0. That's called equilibrium. When the net force is 0, it means the acceleration is 0. Okay, I know that. Okay, I know that because of the stupid page. There we go. If I had an object here and I was pulling on it with a force of 20 newtons, but friction was pulling back with a force of 20 newtons, it means I'm not moving it. It'd be me doing this, right? And it's not moving. I'm pushing, but it's still in equilibrium. It's not moving at all. So if the net force in the x direction turns out to be 0, 20 minus 20 is 0. Therefore, I can conclude that there's no acceleration and that the velocity is constant, or it's at rest. Either one of those 2 cases can occur. All right, please review sections 4.1, 4.2, and 4.3. Look at your notes, look at the conceptual stuff, and then look at a mathematical example from section 4.3. Be able to draw a free body diagram. That's like a given, easy points. But be able to do it. You did it with your homework. You did it in class several times. You're just drawing the forces acting on an object.
In free body, do you draw all the forces, or only the forces that actually end up moving?
The forces that are acting on that object. On that object. Any force that affects that object. Okay?
Third, fourth, and fifth.
Look at my schedule, see which ones I have for you.
I'm scheduled on.
Do you have class right now?
Yeah, but I've got.
I don't have it on here.